active particle. Okay? And so if a mole is a measurement of some type of molecule, more specifically, an osmol is a measurement of a certain number of molecules, but those particles are osmotically active. Okay? What we mean by that is osmotically active particles are those that draw water towards themselves. Okay? So under this sort of thinking of this sort of definition, osmolarity is a measure of the ability of a solution to attract water. Okay? So this is very, very basic, I guess, a little bit too rudimentary, but we could say ability to attract water. Okay? And we're attracting water on the basis of the number of osmoles we have. Okay? So if we say this compartment has a certain number of osmoles per liter, and another compartment has more osmoles per liter, each of them are going to be sort of drawing water towards themselves, but the one with more osmotic particles will draw water to itself, away from the other side. Okay? So this is not exactly, we often learn about osmolarity as sort of diffusion of water, right? Osmosis is the diffusion of water. Right? How many of you have heard that? Yeah, okay, but it's not. But it kind of works in a different way, but conceptually, yeah, you're moving from a high concentration of water to a low concentration of water. But it's the number of particles that draw water in. Okay, so solutes have the ability to draw water towards themselves. Okay? And the more, if you have two chambers, the one with more particles, solutes, is the one that has the greater ability to draw water. So water moves towards more solutes. Okay? So in a very rudimentary way, we could think of osmolarity as an ability to attract water, but this is based on the number of osmoles. Okay? So another way of thinking about this is its number of osmoles per volume. Okay? In other words, solute concentration. Right? The greater the solute concentration, the greater the ability to draw water. Okay? So these two are not exactly equivalent, but we can. These are two operating definitions for osmolarity. Right? A solution's ability to draw in water, and we know that this is dependent upon the number of osmoles per volume. Okay, so you've all seen these, in every textbook there's this U-tube, right? You have a question? Sorry. It is pure number, so a particle is either osmotically active or it's not. Yeah, and that's mostly based on size, right? So in the body, if you think about an ion or a small organic molecule or a protein, these are all osmotically active particles. Okay? A blood cell is not. It's huge. It doesn't have an effect because of its size. I don't have the answer to, is there a point where it's kind of in the middle and maybe less of an effect? I don't know, but it doesn't really seem to have a practical effect. Yeah, but you would think that there might be. So this is called the U-tube, right? Weirdly, right? And you've seen these. Have you ever seen one of these in the book before? Yeah. How many of you have ever seen one in real life? No, nobody. They only exist for this purpose, for illustrating this concept. I think they really do exist, but I've never seen them. All right, so we've got two solutions here. One, on the left here, it has fewer particles. The right has more particles. Okay, we've got some semi-permeable membrane that is only permeable to water, but not particles in the middle. Okay, and you can see that we have them labeled at the top with their osmolarity. Okay, so osmolarity is measured in osmoles per liter. So this is milliosmoles per liter. Okay, and you might see this written without the O, right? The OS, it just might be millimolar, but here's milliosmolar. most of the time it doesn't matter, okay, they're equivalent. We're basically measuring number of particles per volume, so it's concentration. Okay. We can use terms like hypoosmotic and hyperosmotic to describe the difference. Okay. The one on the right is hyperosmotic to the other one. The one on the left is hypoosmotic to the other one. Okay. These are the terms I'll prefer to use. There's some words like hyper and hypotonic that we'll talk about in a little bit. This has specific application to cells, so these are a little bit more generic terms and we'll be using them mostly, okay? So, pretty simple, right? Hyperosmotic, it's got more osmotic particles, a higher concentration. Okay, so what happens if we allow water to exchange? What's gonna happen? Water's gonna move, yes? Which way? This way, to the right, okay? Let's use those two definitions. If we think of it as diffusion of water, there's more water on the left than the right, and we're gonna diffuse to the right, okay? A little bit more accurately, we could say there's more particles on the right that are drawing the water in, okay, than those that are being drawn to the left, right? So there's gonna be a net movement of water towards the right, however you think of osmolarity, okay? However you think about it. The effect is we're going to see a movement of water across that membrane until what? Until when? When will it stop? No, the concentrations are the same. Concentration of what? Of water, of the solutes, either one. Okay. We're going to have a movement of water until, there we go, until the concentrations are the same. Okay. Osmolarity is now the same. Concentration of water, concentration of particles. Well, that's the same, okay? So water will move until the osmolarities become equal. If we want to know how forceful this happens, this is where we encounter another term that's related to this, which is the osmotic pressure. Okay? So, conceptually, an osmotic pressure is the force at which water is moving from one side to the other. Okay? It's the force at which water is moving. Okay? Now, we can't measure this directly, but we know for every force is an equal and opposite force, right? So the way that we can measure this hypothetically is if we try to stop that movement of water from happening. Okay? So if we went to the state, if I back that up a little bit, if we went to a state where we were to apply some pressure on the right, apply some positive pressure here. Let me not do that. Well, confuse anybody with charges, right? So we put a plunger in here and we're gonna push down on it and prevent that movement. We can do that. Okay. And this is one thing that separates osmosis from diffusion, right? You can't do this diffusion, but when you're talking about this solvent, the water here, you can apply a force which is going to be equivalent to the osmotic force. Okay? The osmotic force is going to be pushing, osmotic pressure, excuse me, is going to be pushing to the right, and we're creating a force to the left, right? And the degree to which we have to push back can help us determine the osmotic pressure. Okay? Osmotic pressures are important because when water moves, and it's because of the osmotic pressure that it's moving, things happen. Water leaves capillaries and accumulates in the interstitial fluids. Okay, and so this is an important concept. Okay, but it's a result or a byproduct of osmosis. This osmotic pressure results from osmosis. Okay. Any questions on this? It's kind of a weird concept. Okay. Okay, next thing. We can use terms like hyperosmotic, hypoosmotic, isoosmotic to describe things that are equal, right? There's a certain tonicity that is particularly important when we're thinking about the effects of osmosis on cells, okay? This is something I probably won't use a lot in the course. I prefer to use hyper and hypoosmotic, because it's a little bit more generic, but this is incredibly important clinically, so I want you guys to be familiar with this concept. What time are we done, by the way? 1:45? Okay. Thank you for not lying to me. All right, so what is tonicity? Tonicity is describing a solution, and because of its osmolarity, that solution's effects on cell volume. Okay? So, this is the typical situation where you might encounter this, right? Grandpa here is getting an IV. They put everybody on an IV if you go to the hospital. Is everybody volume depleted? I don't know. But anyway, you go to the hospital, and they're going to hook you up to an IV, and it's going to be probably 0.9% sodium chloride. Okay? This is considered isotonic saline. You heard that term? Isotonic saline. It's also isoosmotic, meaning that when we're comparing this to what's already traveling through your blood, the blood plasma, it's got the same osmolarity. Okay? And in fact, your blood plasma is also mostly sodium chloride, but it has some other stuff too. But sodium and chloride are huge components of what's in your blood plasma. Okay? So if we put more of that same solution, that same concentration of solution into your blood, right? Is it going to have any effect on your blood cells that are traveling in that blood plasma? What do you say no? No, okay. So our blood plasma has an osmolarity. This is an approximate number, okay? If you're a good student, you'll remember 300 millimoles per liter. Okay, we could also say 300 milliosmoles per liter. Same thing. Okay, so blood plasma has 300 milliosmoles. You need to remember that. Okay. If you're a really good student, you'll know it's about 395, not 295. Okay, inside of cells, it's about the same. Okay, now the ions that make up what's in there are different, of course. But if we measure all of those particles, and all those particles behave osmotically the same, we would say that the addition of saline, when it mixes with your blood plasma, is not going to affect your blood plasma, and so therefore, the osmolarity of the blood plasma is not going to be substantially different from that of your red blood cells. Okay? So, we would call this an isotonic solution because it does not affect cell volume. Right? So these, whatever tonic, isotonic, hypertonic, hypotonic, they only have to do with cell volume. Okay, but it's related to their osmolarity. We could also say it's isoosmotic. Okay, that's no surprise. Okay. All right. Now they look worried. We've doubled our saline, 1.8%. Don't ever do this to somebody. But what happens? We're dumping 600 millimolar saline, 1.8%, into the blood plasma. So the blood plasma osmolarity is going to go up, right? Okay. So our blood plasma is going to go north of 300 milliosmoles, right? You see that up there? And the cells are not going to change, right? Our cells aren't going to change as a result of this. Okay. There's not free movement of ions across the cell membrane. So what's going to happen to our cells? Is water going to go in or go out of our cells? Water goes out. Okay, what's going to happen to your cells? Okay, so we call this a hypertonic solution. Right? It has a higher osmolarity, higher salt concentration than our cells, and it has the effect of sucking water out of our cells. Okay. So when you go to the hospital and get some blood drawn, they'll run a hematocrit. Right? What's a hematocrit? You remember learning about this or know about this? Hematocrit. It's measurement of something in your blood. Centrifuge blood. Yeah, it's somebody said there's it's a measurement of your red cell volume. A normal hematocrit is somewhere, let's say 40%. Okay. Depends on who you are, but about 40%. Okay. So 40% of your blood is made up of red blood cells. Okay. What happens if your blood plasma is hypertonic? What's going to happen to that hematocrit value? It's going to go down, right? So it's going to appear as if you're anemic, perhaps, right? Okay. So these blood plasma concentrations that affect your cell volume can affect clinical measurements, okay, that we rely on to decide whether there's something wrong with somebody. Okay. So hypertonic means the cells shrink. Okay. All right. Now, what if we just give them plain old water, right? Let's throw some plain water into your veins. What's going to happen? It's going to lower the blood plasma, right? And now we're going to have a blood plasma less than 300. What's going to happen at your cells? Water's going to move in, right? So cells will take on water, okay? And we'll describe that as hypotonic, right? They're going to get big, right? Your hematocrit or your percent red cell by volume is going to go up. Okay? All right, so hypotonic means the cells swell because of the solution that's applied. Okay. So hypertonic, hypotonic, isotonic, all of these describe the fluid on the outside of our cells and their actions on the cells. Okay? If we're just talking in generic terms, we can also use hyperosmotic for solutions that are saltier, right? Or hypoosmotic, just as well. Okay, so now we've got about 15 minutes left. I want to take this a little bit further. Okay, so you should understand those osmotic principles. And do I have questions before I move on about these things? Nobody's ever going to give you those kinds of values, right? Nobody puts distilled water into a patient that's bad, right? Nobody puts twice the normal amount of saline in it, that's bad. Okay, but you get the idea. Okay, so let's talk about the whole body, right? Let's think about what's going on here osmotically. This is you, okay? When I think about you, this is what I think. You're like this weird set of chambers, okay? You got a mouth hole at the top, water and ions go in, right? And through your digestive tract, the water and the ions end up in your blood plasma, right? And you got a urinary system where you lose some of those ions of water. Okay. So what you eat and drink, they're sort of residing in your blood plasma for a time, right? And we regulate these things and make sure that the plasma volumes are within normal homeostatic range. Okay. We also have some other fluid compartments in the body. Okay, so there's the blood plasma. That's one. Another is the interstitial fluid. Okay, it's a term we're going to be using a lot in this course. We should learn it. What is interstitial fluid? I know we're talking about it. What is interstitial fluid? Anybody have a guess? Yeah? It's the fluid between your cells, right? That does not include your blood plasma. Yes, that's what you said, basically. So it's the fluid, not our plasma, okay? But it's the other extracellular fluid that we have in the body that is between our cells, okay? So all of that fluid that's bathing your cells. And we keep this separate from the plasma. And what separates them actually, we keep them separate in our mind, but what actually separates them is the capillary wall. Okay? So blood is contained within blood vessels, okay? And at the capillary wall, there's the opportunity for exchange to take place. Okay? And what can happen through that capillary wall? Well, water and ions can freely move, right? Because capillaries have big spaces. Some not as big as others, but there's the free movement of fluid, water, ions across a capillary wall. Okay? So whatever happens in your plasma is going to happen in your interstitial fluid as well. If you eat a bunch of bananas and your potassium goes up in your plasma, that you'll have that same value in the interstitial fluid as well. It's going to equilibrate. It's going to be the same always. Okay? And together, these make up the extracellular compartment. Okay? Extracellular compartment. We have a cell membrane, lots of them actually, but we have a cell membrane that separates this extracellular fluid from the intracellular. And this is where we have a lot of difference between the composition of those solutes, right? So if you look at the top, 300 milliosmoles per liter, 300 millimolar. On the left, 300 on the right, they're the same. Okay, same osmolarity roughly. Okay, but what's in the intracellular compartment, right? You got tons of potassium and phosphate and these sorts of things, and very little sodium and chloride, right? And it's the opposite outside of the extracellular. But if we just add up particles, they've got about the same osmolarity. Now here we have a lot more of restriction about what can move. Okay? Most cells in your body have very little permeability at all to water when it comes to the lipid bilayer. However, how can they get through? How can water get through? Aquaporins. Okay? So lots of aquaporins in most cells of our body. Okay? When we get to kidneys, we'll talk about some cells that don't have aquaporins, but mostly we do. Okay? So water can equilibrate here very easily. What you don't see equilibrating very easily is salts. Okay? So we cannot move sodium chloride through the cell membranes of our cells. Okay? Yes, we've got ion channels that allow some leakage, but due to chemical and electrical forces, this is a really small number of ions, right? So if you pack the outside of our cells full of sodium, that doesn't mean we're going to get more sodium inside the cells. Okay? So what we've got here, essentially, if we kind of get down to a very basic system of looking at this, a little bit rudimentary, but it helps us to visualize what's happening. We've got an intracellular compartment and extracellular compartment of roughly equal osmolarities. Okay. So, understanding this is kind of important for understanding what's happening in the whole body. That's kind of what we've been leading to. What if we have an excessive accumulation of water in the body? Okay, so this is not just drinking, 12 ounces of water, but continually pouring water into you. Okay? Maybe somebody tells you you're supposed to drink 2 gallons of water a day, and you're trying, okay? Or you're in a water drinking contest. Don't do that. But you're pouring more water into you than you should. Okay? What's going to happen? First off, is this going into your intracellular compartment or your extracellular compartment? Extracellular, right? Goes in through your GI tract, absorbed by your plasma, and spreads out into the interstitial fluids, right? So what's going to happen to your extracellular osmolarity? It's going to go down, right? It's going to go down. Okay. All right, so your extracellular osmolarity is going to go down. What's going to happen to your balance of water across those compartments? Is water going to do anything? Is it going to cross over into the intracellular compartment or into the extracellular? Where's it going to go? Yeah, it's going to go into the intracellular compartment. Okay, and this is about 2/3 of your body's mass, right? It's a big chamber. So if you're constantly taking in lots and lots and lots of water, some of that water is not just going to be urinated out, it's going to be pushed into, or pulled in, more accurately, into your intracellular compartment. Okay? So water is going to move into our cells. Okay, so our extracellular compartment has become what? What kind of a tonic? Has it become hypertonic, hypotonic? Hypotonic, right? It's also become hypoosmotic, another way of saying that, relative to the intracellular compartment. Okay, so water is going to move across our cell membranes. Every cell is going to take on water and increase in volume. Okay? So as a result of this, we can observe some changes in the body, right? And this little purple line is meant to illustrate the change relative to the initial position. Okay? So you have volume across the bottom. Okay? So we can see that because we're constantly taking on water, our extracellular volume is going to expand, our intracellular compartment is going to expand in volume, right? You're getting bigger. Right? What's happened to your overall osmolarity along the y-axis? What's happened? Yeah, your intracellular and your extracellular osmolarity is going to attempt to balance, right? So, because due to the movement of water. So, what's going to happen as a result of this excess water is that your extracellular and intracellular volumes expand and your osmolarity drops. In particular, we care about this, and we care particularly about the extracellular compartment. Why is volume change to the extracellular compartment important? Think about the whole body, the systems of your body. Do any of them care about volume changes? Yeah.
Your blood pressure?
Blood pressure, yeah. What's going to happen to your blood pressure?
It's going to increase.
Yeah, it's going to be increased, right? You have more blood volume. Okay, extracellular part of this is blood. Okay, so your blood volume is going to go up. Okay, and your blood pressure is going to go up. Right? And everything that is affected by blood pressure, kidneys, right? These sorts of things. What if you're a brain cell? What happens to if you're a brain tissue and you start to swell? Why do we care about that? This is an intracellular expansion, but what's wrong with brains expanding? Yeah?
There's only so far you can go.
There's only so far you can go, right? We all think bigger brains are better, right? But if you're taking on water and your cells are enlarging, your neurons, etc., there's anywhere in your body, okay, you can get a little bit juicier, right? No problem. Right? Take on more water in your muscle cells. But in your brain, there's nowhere to go with it, right? So bad things can happen to you if your brain cells enlarge. Okay? So drink water. Don't drink too much. You can be paranoid about this. We don't have a lot of time, but I want to just bring up this one other option here, and there's a couple of other scenarios at the end of the slides that I want you to think about. I'm only kind of abbreviating these concepts. So here's another scenario. Okay, you've got this hormone aldosterone. Remember that? I don't think so. Okay, aldosterone is responsible for elevating sodium levels in your body. Okay, it does so by acting on your kidneys, helps to reabsorb sodium if that rings any bells. And so as a result of, if we have too much aldosterone, it's called hyperaldosteronism, we're going to have too much salt accumulate in the extracellular fluid. Okay, what's going to happen? What happens? So first place, what happens to the extracellular osmolarity? It's going to increase. Okay. As a result, what's water going to do? Yeah, water is going to move from intracellular to extracellular. Okay, so you're going to be draining water from your cells in order to maintain osmolarity. Okay, you're not doing this on purpose. Okay, so when I say in order to, I don't mean that you're doing it on purpose, but you are the effect of osmosis is going to be that you're going to move water into that saltier chamber, right, into the extracellular. So we get an extracellular volume expansion, just like when we're pouring water into our cells. Okay. But what's happened on the other side? Intracellular volume is shrinking, right? Where's it going? In your blood, into your extracellular fluids. Okay. And so both of these have, as a characteristic, extracellular volume expansion. Okay. One is due to too much water. The other is due to too much salt. It seems a little bit paradoxical at first, right? But if you realize, in one case, we're pulling water into the extracellular fluid with salt. In the other case, we're adding water to the extracellular fluid through drinking. Okay? So make sure you can understand what's happening here. Blood pressure is kind of an important thing, right? And it depends pretty heavily on that blood volume. Okay, we'll start next time with a quick pull everywhere.